Hey, I wanted to take a minute and go over some of my answers, or one possible set of answers for this writing assignment that I gave you pertaining to based on the emission spectra demonstrations. So, as you probably have already submitted your answers to these questions in your own handwriting and had another of your colleagues, your classmates, review what you wrote, let me give you one possible set of answers. If I look at the equation first, E equals h nu, the energy of a photon, or energy associated with a particular frequency or wavelength, I can solve for wavelength as Planck's constant multiplied by the speed of light and also divided by the energy associated. Small number of joules, but still, Planck's constant is even smaller. Comes out to a small number of meters. Waves of light are very, very small. And if I change that from 10 to the negative 7 meters to 10 to the negative 9 meters, like, why would you do such a thing? Because 10 to the negative 9 is a nanometer. I can see that the energy associated, the wavelength associated with this 3.03 times 10 minus 19 joules of energy is 656 nanometers. And if I were to refer to a chart something like this, 656 nanometers seems to be matching with the red color, which happens to be emitted or absorbed by a hydrogen sample when an excited state electron from level 3, transitions down to or into transition energy state 2. So if I were to cartoon that, if I look for, like, say, a nucleus here, a long ways away, energy level 1, the ground state of hydrogen electrons. Oh yeah, what was the wording here? Transition occurring in a hydrogen atom during the absorption of a photon of energy yada. So it looks like for that hydrogen atom to absorb such a photon, it might match with an electron going from 2 to 3. If it were to emit that, it would be going from a 3 to a 2. That's why I drew my electron here first and said it's going to transition from level 2 up to level 3. Level 3 is higher in energy because it's further from the nucleus. And I wrote absorption there. Isn't that cute? Of course, there's dozens of different ways you could have cartooned this, so hopefully the person that reviewed your paper told you good job or asked you a good question for clarification about what you drew. The next question, oh my goodness, I don't know I think it has a good answer, but this is not a good answer. If I had a tube full of mostly hydrogen gas and a little bit of air, what might that emission look like? Well, this is what I originally thought, although I think this page is wrong. I'll show you a page I think might be better. But, depends who you ask, or if it's been tried, I don't know. So I was thinking to myself, hydrogen emits in the visible in a kind of a purplish, a bluish, a light blue, a green, a red. So I was thinking maybe 4 distinct emissions from a hydrogen sample, 90% hydrogen in the bulb. So I might see this wavelength, and this wavelength, and this wavelength, and towards the purple and blue. But there's also some air in the bulb, and if the air gets excited sufficiently, perhaps it'll give off its particular colors. What should I say? Spectrum? What does air emit when it gets excited? What colors? What electromagnetic radiation? Which photons? And the answer is I didn't know when I drew this. I'm just imagining. So I was hoping, praying, incorrectly so, that the air might emit so many different colors that it might look almost like a continuous spectrum. Like it would emit this color, and 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 this color. It would emit so many colors that I couldn't really tell it was a discrete emission, but rather a whole bunch of different wavelengths of light. And so if I were to add this bump to that bump, add this, and a spike of this, and a spike of this, and a spike of this, that I might actually see something like Mm, 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 mm. Maybe. The point here is that I'm going to add together the emission that I would expect from hydrogen to the emission I would expect from air. Then I thought to myself, well, wait a minute, air is comprised mostly of nitrogen and oxygen. So what if I had a hydrogen emission, which is this, combined with, say, an air, uh, an air sample of air? Well, we have to carefully kind of match up these frequencies because I don't think this 500 exactly falls even with this one, and I don't think this 700 exactly falls even with this one. So I kind of said, well, let me lay one on top of the other one. Oh, by the way, also, what is air comprised of? Isn't it comprised of oxygen, which has a peak at about, what's that, 740? So a peak at 740. So this peak matches with this peak. So this peak in the emission of photons from excited air, which air contains oxygen, so this peak is this peak. This one's off the charts up here. This peak for air at about, what, that's 660 or 70 is probably this peak right here. The heights of these peaks are a little bit nebulous because how tall is it going to be? Kind of depends on the intensity of the of the emission. So that can vary quite a bit. Or if I compare nitrogen, these are the nitrogen emissions. So some of this bumpiness is likely included in some of this bumpiness. So some of these bumpiness, that's from the nitrogen. I'm pretty sure this peak and this peak are from the oxygen in the air. Interesting. So anyway, the bottom line is I think there's a better answer. What if I combine the distinct hydrogen peaks like this one and this one and this one and this one with the air emission, this one in light blue? If I were to add those two together, perhaps I might get a better answer, something like this, where I have the nitrogen bumpiness. Some of this was oxygen as well. I don't remember which was which at this point. I could look back up and see what the frequencies were. But if I had a whole bunch of hydrogen in my sample, I'd be giving off, what was it? I think this is due to the oxygen, isn't it? Anyways, these are additive. If I have a whole bunch of different junk in a sample getting excited, then the colors I might expect to be given off when that sample gets excited is the sum of all of them. The last question is a tricky one, and I'm not sure I have a complete answer because it would take much more space than I allowed you on your paper. The answer is, well, it depends on how you define chemistry and how you define physics. If you define chemistry as old bonds breaking and new bonds forming, then I'd have to say that when an element or pure substance is stimulated to produce an emission spectrum, physical or chemical process? Well, if it's an element all by itself, it's definitely a physical process. But if it's a pure substance, like some kind of compound with some structure, it's possible that it could on occasion break bonds or even react or interact that with something in the air. So if I define, down here in blue I said, if I define chemical change to be old bonds broken and new bonds formed, then I'd have to say that usually the excitation of a sample to give off its electromagnetic waves, photons, an emission spectrum, is usually physical. But in some cases, down here I said, in some cases, especially if you're doing this in air or with any other substances, I should go back, I just remembered something. Yeah, I might on occasion see some chemistry. Sometimes in cartoons, in diagrams, we'll say pure substance, whatever it is, you excite it with some HV, some H news, some photons, and I get a same pure substance, but some of its electrons have been bumped up to an excited state, and that little asterisk, how do you pronounce that, is denotes an excited state. So the electrons have more energy than they usually do, and they don't stay there for like a few picoseconds, sometimes nanoseconds, but they release that same, probably the photon of the same frequency in just a brief time period and fall back down to their original state. Of course, if more of these are continually bombarding the pure sample, then that pure substance again gets excited and it relaxes, and excited and relaxes, and excited and relaxes, and excited and relaxes, and every time it relaxes, it gives off that related, if not exactly the same, frequency. What else did I want to say here? Yeah, so it's possible to see some chemistry, but many, many times we're just talking about a physical change that we can use to work backwards and try to figure out what in the world is this pure substance doing, or how is it, put together. Okay, yeah, so that's the chemistry. Sometimes a compound, like if it's really a large molecule, can break apart easily if it's exposed to especially ultraviolet radiation. Ultraviolet photons have lots of energy and can therefore decompose things. I wanted to mention this question here has a much simpler answer, and if anyone thought of it, congratulations, you're thinking globally. Sorry about this. Right here, this question: sketch the emission spectra you would expect from a special bulb containing 90% hydrogen and 10% air. Of course, 10% air, in that sample of 10% air, of that air, 20% of it is oxygen. So you might have answered there's enough oxygen there in the air to actually combine with hydrogen to make water. You'd have your light bulb explode, and if it exploded, you might not be able to coax the emission spectrum out of it. That's a good answer. I could see it totally. So in any case, thanks for thinking about this, and I'm looking forward to reading all your responses. See you in class.